guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my discussion today. And I'm going to look at a concept in mechanics, which is basically the aspect of acceleration. Now, in our previous video, we had defined a range of terms ranging from displacement, velocity, average velocity, instantaneous velocity, and the concept of acceleration, whereby we defined this specific concept of acceleration as the rate of a change of velocity with respect to time. Now, we had this particular representation whereby we had this specific aspect of acceleration given in terms of a ratio, which was given as a change in velocity. So I'm going to give this one as such, and then a change in time given as that one. So we had this one represented in terms of A, which we said acceleration is basically a vector quantity. So we can give it in terms of this specific representation. So the change in velocity is the difference between the initial and the final velocity, whereby we accept that if we have the graph of velocity against time for these two Cartesian coordinates, then we're going to have this a specific aspect of change in velocity against time in case we have a constant acceleration. So I'm going to elaborate on that one. So we're going to define this one by having the ratio between the change in velocity against a change in time given as that one, whereby if we take this specific aspect of acceleration at a point perhaps A and B, then we can find this specific ratio by a value over v at this specific point coinciding with the value over t at this specific point. And then we're going to have another one at this specific point for b, which is going to be given in terms of t2, and then we're going to have a v2. So the ratio between the difference of the change in y-axis, which is a v1 v2 minus v1, and of course the ratio between that one and t2 minus t1 is going to give us the aspect of acceleration. So therefore we can represent this one as the change in velocity, which is a v2 minus v1 divided by t2 minus t1 given as that one. So this one can be given in terms of a delta v or over delta t, and that is going to imply our concept of acceleration. Now in this case, we are going to look at other ways in which we can represent this aspect of acceleration, especially now that we had talked about the concept of instantaneous acceleration. So this is going to be an acceleration which is going to be described at a particular point. So we're going to have this one given as instantaneous acceleration given as that one. So this aspect of instantaneous acceleration is going to be this specific ratio, which is represented as the change in t, which is of course change in time tends to 0. So we shall have this specific aspect of instantaneous acceleration given as the limit as the change in t tends to 0 over this aspect of delta v over delta t given as that one. Of course, it's going to be giving us instantaneous acceleration. So this one can be given in terms of dv over dt, which basically implies the change in velocity over time. And then this one still can be given in terms of this specific derivative now that we have introduced that differential. So we're going to have this one given in terms of dv. So v, we had said basically is going to represent velocity, which is basically the ratio between change in displacement over change in time. So if we take the second derivative of a change of a displacement with respect to time, so this is going to be a change of displacement with respect to time for the first differential, and again the result of this is going to be given a second differential, and therefore this is going to be giving us the second differential of this d over dt. The square of that one is going to be giving us instantaneous velocity given as that one. So we're going to see that in case we consider the acceleration as a constant value, then therefore we can represent this aspect of instantaneous acceleration as an equal value for the average acceleration given above. And this also is going to be the case for the concept of velocity, which we have looked at in our previous video. Now in this particular case, we can have this specific representation for the graph. And this is going to be giving us a graph of velocity against time given in terms of t. So in this case, if we find a specific point of this one, in order for us to evaluate the concept of acceleration, we're going to take a tangent line at this specific point. and then that is going to assist us evaluate the change in t over change in of course v, given as that one, which is going to be the ratio between delta v over delta v, delta t giving us a particular point of acceleration at that particular point which we have just mentioned. So this is going to be assisting us in trying to do different evaluations in our subsequent videos, whereby we're going to use these two basic ratios which I've defined on the board in order for us to find the concept of acceleration. Now, suppose we have perhaps an object that is going to move using this specific expression. So we're going to use this specific expression and see what are some of the ways in which we can define this specific aspect of acceleration. So I'm going to have an object moving according to, of course, this formula, whereby its displacement can be defined in terms of b plus c and the square of t given as that one. Or let's have so this is going to be a cube. So this is going to be an object that is moving, and it can be described using this specific formula. Now, if we are required to find its instantaneous acceleration at the time t, then we can, of course, work on this formula from the previous discussion which we had. And I'd said that instantaneous acceleration is equivalent to the delta, of course. So we're going to have this one. Instantaneous acceleration is equivalent to a delta v over delta t over delta t, and this is going to be given in terms of a dv over dt, given as that one. So we had said that this, of course, is going to be still given in terms of a d over dt over the first derivative of displacement with respect to time, and that is going to be giving us a second differential of this specific aspect of course, the object that is described using this specific equation. So for us to find the first derivative, we're going to find dx over dt, which is going to be giving us a d over dt of this value of b plus c t, and that one. So these two are basically going to be forming our constants, but this is a coefficient of this specific value for t. So we're going to have this one given in terms of 3t squared, and then we're going to have a c given as that one. And therefore, that's going to be defining what we refer to as our velocity. So our velocity is going to be the first derivative of this specific type of displacement given by the equation. And then we're going to find our dv over dt, which is going to be, of course, the derivative over d of 3t squared c given as that one over dt given as that. So this is going to be giving us a 6tc given as that one, or a 6ct given as that one. And this is going to define what we refer to as our instantaneous acceleration, which we have given in terms of this specific second derivative of this displacement which we have given above. So in case we come across the various range of course, formula or description for motion of objects given as that one, we're going to use the same strategy in order for us to find this concept of acceleration, which I've just shown using a simple example on the board. So in this case, we're going to look at the second illustration which I've given on the board, and this is going to be still a graph of velocity against velocity against time given using this specific nature. Now this graph is going to be having 4 points for A, B, C, and D, which basically is going to be describing the relationship between the velocity and time of an object that is undergoing motion. Now from the first point of A, this object is going to be having a positive increase of velocity against time from the point A to B. But we're going to see that this specific point in time, of course, let's assume that this is going to be T1. So at T1, we're going to have this particular velocity of V1 given as that one. But so therefore, we are going to have an increase. So we can describe this specific graph in terms of this, of course, statement, perhaps a short form of this statement which I'm going to give. So between A and B, we are going to have an increase in velocity with respect to time. So increase in velocity with respect to time. But as the motion proceeds from B to C, we're going to have a constant constant velocity with respect to time. And as we're going to move from, so let's say this is as the t2. So this is going to be t0, t0, t1, t2, and then we shall have this one given as t3. So there's a motion between point C and D, which is going to be, of course, a decrease in velocity with respect to time. So in this case, this is going to be what we refer to as a deceleration, which is going to be a negative, of course, a negative aspect of the concept of acceleration. So in this case, this is going to be describing this kind of a motion whereby we're going to have a positive increase in velocity against the time, which is going to be referred to as acceleration. So between A and B, we're going to have acceleration, whereas between B and C, we're going to have a constant, of course, object whereby we're going to have this delta V, or V2 minus V1, whereby we're going to assume at this specific point we're going to have V1, V2 at this point. So the difference between the two is the two are going to have the same value, and therefore we're going to have delta V equivalent to 0, implying that for the ratio of acceleration, which is given in terms of delta V over delta T, then therefore this is going to be equivalent to 0. So there will be no acceleration between B and C, whereas we shall have the change in velocity against time for the last one being a negative one, and therefore we're going to have what we refer to as a deceleration between C and D. So that's going to be one of the ways in which we are going to be describing this particular kind of graphs. And of course, they are going to assist us in trying to describe the nature of motion of various objects, which we are going to come across under the broader topic of mechanics. So that is it for now, guys. Kindly check out description boxes for various links of other videos. Engage us in the comment section, and also ring that notification bell to be getting updates on our various uploads we do in mathematics and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.